Let us now start at looking at equations that underpin the capillary filling, and we will start with the easy case of a cylindrical channel. So, and we're not going to try to model actually the experiment I just showed, except that we're not in this calculation. I'm not going to take into gravity for the time being. I'm just going to look at a channel that is absolutely horizontal and see how that is filling and what's actually going on in such a channel. So let's consider a capillary channel with a solid wall. And I have a liquid droplet here, large liquid droplet here, and I have a capillary filling that looks something like, with the front looking something like this. So this is my solid, this is gas, and this is liquid. Well, what do we know? We know that there will be an equilibrium contact angle theta here. And now the question is, we know also that there's a filling from the left to the right, and we're going to try to write down in formulas where that comes from, that filling. The first thing we see is that we have, of course, a curved surface, curved interface. That means we have a pressure, a capillary pressure. And how large is this pressure? Well, we know that. We know, to start with, we're going to consider any point in the liquid but close to the interface here. All these points, they have the same pressure. Yeah? And all the points on this side of the surface, they also have the same pressure. That's because it's a very small system, so there's no kind of hydrostatic pressure difference or pressure fluctuations. The pressure here is the same in the liquid, and the pressure on the gas side is the same. So I have the same pressure drop in any point. The delta P at any of these points is equal. And that means that the curvature radius in all these points must also be equal. And given the fact that I need a surface that has a circular, the cylindrical channel, so it has a circular boundary, circular triple phase interline, and it has the same curvature at any point, I know that this surface must be spherical. So I know that this is a sphere, and I also know this sphere has a radius, that I can draw here. So this is the radius of my sphere, r. And I know, because this angle, this is a straight angle, so this is also theta here. And if I call this here r tube, or r capillary, I can call it r cap, then I can easily write down that the pressure drop delta P, and I write this equals the gas pressure minus the liquid pressure, must equal, and we have calculated for a spherical surface, you did that as an exercise, equals gamma over 2 times r. And now I also see that r and r cap are related because r times cosinus theta must equal r cap. So r cosinus theta equals r cap. And if I fill that in here, so I know that equals gamma over 2 r cap times cosinus theta. So I have calculated the capillary pressure that drives this flow. Actually, I know the flow goes from the left side to the right side. Time for a little exercise. I have 3 pressures. Can consider pressure here, a pressure P1, a pressure P2 here, and a pressure P3 here. And my question now, my quiz question is, rank these 3 pressures, P1, P2, P3, from large to small. So the largest here, medium, and the smallest. Okay, so the answer to this quiz is rather simple. I know that, of course, I see this is a hollow surface, so I know that P3. Remember the blowing the gas bubble, the soap bubble. Here in P3, the pressure must be higher than in P2. And then I can consider here, actually the pressure just outside here must be equal P3, because this is the gas pressure. I mean, this atmospheric system, these are connected. They're more or less the same height. And I know there's some kind of curvature here, but it's a very weak curvature. So, but still I know that P3, in this case, well, the hollow side, so P1 must be larger than P3, because it's on the hollow side, slightly larger, because this curvature is very low. And I know here that P3 must be larger than P2, so I know that P1 must be larger than P3, must be larger than P2. And now there is something kind of very strange. You know, I see that in P3 here, my pressure is higher than in P2, but still I know that I have a liquid flow Q, volumetric flow Q, that goes from the left to the right. And that seems weird. So how is it possible that liquid flows from a low pressure to a high pressure? There's something fishy about that. But this is only an apparent thinking mistake. I know that if I consider this section here of my capillary, this is a cylindrical channel with a pressure P1 at the entrance and a pressure P2 at point 2. And I know that pressure P1 at the entrance is almost the same as P3 because this curvature is very low. So I have a pressure drop here, and I know that for a cylindrical channel, we have learned, this is the Hagen-Poiseuille formula, that in this case, P1 minus P2 equals Q times 8P mu over distance L, and this is now distance L, times 1 over R cap to the power 4. Yeah, we have derived this formula. So, and this Hagen-Poiseuille formula is true for within the liquid phase. So this is true between point 1 and point 2. So because the pressure in point 1 is higher than the pressure in point 2, I will have a liquid flow from point 1 to point 2. And that is very normal. Yeah? And what happens here between point 2 and point 3? Do I have a liquid flow there? The answer is no. There is no liquid flow. There is an interface, but there is no mass transport across this interface, you know. There's no liquid flowing from point 2 to point 3. The whole interface moves, but there is no liquid molecules moving from the liquid into the gas. Maybe there is a little bit of evaporation or condensation on the surface. That is possible, but is negligible. We are not going to consider that for the time being, because very likely the air here will be saturated with vapor anyway. So there will be almost no evaporation here. So there's no mass transport. So Hagen-Poiseuille is not valid over the liquid interface. It is valid within the liquid, but not over this interface. So yes, it's possible to have a higher pressure here than here, because, and this is not in contradiction, because there is a pressure drop, but there is no mass transport.